Order unless you tell me not to.
Ah, very good. All right, so I'll get started then. Yep, so my name is Noah Lebowitz-Lockard. I live in Philadelphia, and this is my talk on binary Egyptian fractions. So I'd like to start out with some history. I guess if you've attended, some of the last few New York number theory seminars, you've already, seen Mel talk about Egyptian fractions, but I'm just going to review some of the history and background about that. So the Rhind mathematical papyrus is actually one of the oldest mathematical documents we still currently have, dating back from 1550 BC. There we go. Yeah. So it's named after Alexander Rhind. Didn't actually discover it, by the way. He just bought it from someone. So it is kind of, silly. It's just sort of the first person to own it, but got named after him anyway. And he bought the papyrus when he was in Egypt in 1858. Interestingly,
continue.
There we go. It was written by someone named Ahmes, who is actually the oldest author of a math text whose name we still currently have. So that's interesting historical fact right there. Obviously, so predating Euclid and all of the Greek mathematicians whose names we have, over 3,000 years later, we still know who wrote this text. I also like just the first sentence of it is just how I think maybe all mathematical papers should begin. The entrance into the knowledge of all existing things and all obscure secrets. So that's quite a promise, to give at the start of something. Most authors today would not be quite so bold, but just really like that sentence. So the Rhind papyrus, it mostly has sort of standard mathematical facts, a lot of algebra and geometry. But in addition to all that, there's actually something very strange. So in addition to that, there's something very strange, which are 50 different fractions with numerator 2. And each fraction is written as the sum of distinct fractions with numerator 1. So the distinct part is really crucial, right? Because otherwise this would be a trivial problem. You could write 2 over n as just 1 over n plus 1 over n. But once you put this distinctness condition in, it can actually be pretty hard. So here are some examples of fractions they wrote on this papyrus. They have at the start 2/3 equals a half plus a sixth. It's pretty, straightforward. But then they also have these more complicated ones. So Ahmes writes 2/61 equals 1/40 plus 1/244 plus 1/488 plus 1/610. At first, this seemed actually exceedingly strange to me until I noticed that, in fact, these last 3 numbers are multiples of 61. So perhaps if you really thought about it, I guess you could see, how one derives these fractions. So I don't actually know what sort of technique they did to do this, but nevertheless, they wrote these fractions in this way. One possible theory as to why they did this is simply that, in a sense, fractions with numerator 1 are more natural because if you imagine it physically, you're breaking one object into multiple parts instead of breaking multiple objects. So this seems to be the best guess as to this that I've found so far. So from that, this spurred a lot of mathematical interest over the past century. J.J. Sylvester did a lot. Actually, even before, long before that, Fibonacci had done, some research into Egyptian fractions. But so anyway, so the modern definition is this. I'm going to say that a unit fraction is a fraction with numerator 1, and the Egyptian or an Egyptian fraction representation of a rational number is a finite sum of distinct unit fractions. So again, these finite and distinct are really important conditions. Without distinct, it would be pretty easy to write something as a sum of Egyptian fractions. And obviously, if it's infinite, you can just add as many as you want. But this is the modern definition. And so I'm going to talk about some results relating to Egyptian fractions that I find really interesting, and then culminate at the very end with some research that I've been doing recently. Makes this talk a little bit unusual, as it's actually research that I'm currently doing. So I'm a little uncertain about some of the stuff I'll say at the end. There's subject to change, I guess. So anyway, just in general, an Egyptian fraction representation looks like this. M over n is 1 over n1 plus all the way up to 1 over nk, where each of the ni's are distinct. There has been a lot of research into Egyptian fractions. Just to have something interesting here, I have a copy of Unsolved Problems in Number Theory, which is a book, which lists just many different unsolved problems. And in the section about Egyptian fractions, the author lists 4 pages of papers on them. And this is a book from 1994. So, in the past 27 years, there's been even more research into this. But even back then, already a lot of research had been done. In particular, Erdős had done a lot of research, both at the start of his career in the 1930s and then all throughout his career later on. I also typed just the phrase Egyptian fractions into Google Scholar, and it listed 10 pages of results. So as you can see, a lot of research has been done on this subject. So these are just sort of rough, measurements that I did that just, didn't take very long, but yeah. So it's not immediately obvious that every rational number even has an Egyptian fraction representation. Perhaps, you can always approximate these things quite well, but never quite get it exactly. So this is actually a non-trivial result that you can, in fact, write every rational number as an Egyptian fraction, as a sum of these fractions. And there have actually been some bounds on these representations. In 1985, Vos showed that the fraction m over n has a representation with at most a constant multiple of root log n terms. A few years later, Yokota showed that that m over n also has a representation in which every denominator is at most O of n log n double log n to the 4th triple log n squared. So already we're seeing some pretty complicated expressions of these things, which I think, is one reason they're so interesting, that from the simple definition, there's still, a lot of subtle things going on and a lot of interesting mathematics one can do with them. So for the rest of this talk, I'm actually going to talk about binary Egyptian fractions. So that's a representation as a sum of exactly 2 distinct unit fractions. So what's amazing is that, this is, a very restrictive definition, but there's still a lot you can say about it. And presumably anything you find about binary Egyptian fractions, you could try to generalize to Egyptian fractions in general. Throughout this talk, I'm also going to abbreviate this as BEF. That's not, I don't think, a standard abbreviation, but I'm just going to use it just because it gets sort of tedious to write binary Egyptian fraction over and over again. And so a binary Egyptian fraction representation is just m over n equals 1 over n1 plus 1 over n2, where n1 and n2 are distinct. And so, yes, so even with this restriction, there are many notable results. And so I'd like to just sort of give an overview of some results about these that I think are particularly interesting. So do all fractions even have binary Egyptian fraction representations? Well, we saw that every fraction has an Egyptian fraction representation, but this actually turns out to be a little bit too restrictive. So they don't all have these in general. In 1966, Rav found an interesting condition as to when you can actually write these representations. So Rav stated that the following: let m and n be co-prime, the number of binary Egyptian fraction representations of m over n is equal to the number of pairs u and v with u and v co-prime, and also u plus v a multiple of m. And the reason this result is interesting is that it sort of allows us to do proofs relating to binary Egyptian fractions, that this is a condition on the divisors that we can then manipulate much more easily than we can manipulate the definition of binary Egyptian fractions. And the proof, I mean, I guess this is an oversimplified version of the proof, but it still gets at the general idea. So let's say that u plus v is a multiple of m. So I'm going to say that u plus v equals bm. And because u and v are co-prime, uv is a divisor of n. So we can write n equals cuv. So we're defining b and c in this way. So then we can write the following: m over n is bm over bcuv, just by the definitions of b and c. So I'm multiplying the numerator and denominator by v or by b.
Sorry, I've stupid questions. What first of all, u and v are relatively prime, right? Then you said uv is a divisor of, I lost something there.
Oh, of n.
Why is that?
Oh, well, just because so u and v are both divisors of n. And they also just consist of distinct prime factors. Or I mean, sorry, like the set of primes going into u is, disjoint from the set of primes going into v. So right, so just because u and v are.
Why is u? I missed something. Why is uv a divisor of n? Sorry, I missed something here.
Oh yes, so it's because u and v are both divisors of n, and also u and v are co-prime. So it's this co-prime condition that's giving that to us.
You also mean that 1 over u plus 1 over v is equal to m over n.
What?
Sure. Right, fine.
Well, I guess
you're assuming, of course, you're assuming. I mean, you're assuming that one over.
I'm assuming that. I mean, I think the only assumptions I'm making are that u and v are co-prime, right?
Well, then that would not follow from that uv is a divisor of n.
No, oh, sorry. I meant to say that. Oh, you're right. I actually meant to say that u and v are both individually divisors of n. I forgot to put that in this theorem.
So the assumption, it's in the assumptions, but not stated. Okay.
Yeah, I just forgot to. That's true. I forgot to put that on the slide. So yeah, so u and v are co-prime divisors of n. Okay. So yeah, it's a good catch there. But anyway, so once we have that, then we can write m over n as this sum of fractions. So I'm using the fact that u plus v is bm. And so now I have u over bcuv plus v over bcuv. There's cancellation. So I guess I switch the order of these fractions at the end, but it's still 1 over bcu plus 1 over bcv. So given these two divisors, u and v, we have an Egyptian fraction. We have a binary representation. And with some more work, you can show that this is actually a one-to-one correspondence, that for every pair uv, there's exactly one pair of these fractions and vice versa. So given these fractions, you can define u and v as, I guess, you divide both of the denominators by the GCD, you'd get u and v out of them. And yeah, then you could get b and c. But again, I think this is just a really nice condition And the fact that it follows very nicely just from the definitions and a little bit of algebra is, I think, very pleasing. And so this actually also has a nice corollary. So the fraction m over n has a binary Egyptian fraction representation if and only if the denominator has two co-prime divisors u and v such that, well, m divides u plus v. So I'm just saying that you can find such a pair.
Do you need the restriction that u and v are multiples of n or divisors of n, the one you omitted in the last slide? Do you need that here also?
So this time I actually remembered to put it there. So I do have n has two co-prime divisors, u and v.
Okay, so, I didn't notice that. Okay, thank you.
I remembered it once. Yeah. Yeah. So
I see the denominator has two co-prime divisors such that the numerator divides it, right? The sum, right?
Yeah. So it's certainly a strange condition. I remember a long time ago, someone giving me one piece of advice about number theory, and that was that addition destroys structure. So, we have u and v are divisors, and then u plus v is just this number that comes out of it. Yeah, there it goes. So here's an example of this corollary in action. And we're going to start with n equals 14, and we're going to find all m co-prime to n such that m over n has a binary Egyptian fraction representation. And of course, because n is small, we could do this by brute force if we really wanted to, but I think this is a nice application of the previous corollary. So I'm going to list each pair uv of co-prime divisors, and then I'm going to list all the divisors of u plus v. So our pairs are 1, 1, 1, 2, 1, 7, 1, 14, and 2, 7. And so, well, 1 plus 1 is 2. So the divisors of u plus v are 1 and 2. Second row, the sum is 3. So we have 1 and 3. Then 8, 1, 2, 4, 8. 15, 1, 3, 5, 15. Finally 9, 1, 3, 9. So then I took out all the m that actually do share a divisor with n, and then left with this list. So 1, 3, 5, 9, and 15. So those are the only ones that have binary Egyptian fraction representations. And here are examples for 2 of them. So 5/14 is 1/3 plus 1/42, and 9/14 is 1/2 plus a 7th. And so this argument shows us that, for example, we can't write 11/14 or 13/14 as a sum of 2 distinct unit fractions, which again, one could show by trial and error, but also comes out of this little argument right here. So for large n, this would be a faster method for writing out every binary Egyptian fraction that we can. So, you'd still have to factor n, but that's still much faster than, checking every possible numerator. So here are some neat little results about how often the fraction m over n has a BEF just in general. So suppose you fix m, then in the long run, m over n almost always has one of these representations. So the first theorem about this is due to Hofmeister and Stoll in 1985. So let's say that E sub m of x is the number of n less than or equal to x for which m over n does not have one of these representations. Then E sub m of x is at most a constant multiple of x over log x to the 1 over phi of m. So this phi is the totient function. So the important thing, right, is that you still are dividing by a positive power of log x. So this quantity is little o of x. So m over n really does almost always have one of these representations. This was improved by Elsholtz.
When you say almost always, you're fixing m and letting n grow.
Yes.
I mean, what happens if you let M and N both grow?
So then you actually, yeah, so that is actually on the next slide. So
Right, sorry.
I guess I haven't been very precise, but actually, yeah, the opposite happens, just to spoil that. So if you fix N, typically almost all M don't work. So this is,
but I wasn't asking that either. I was asking, suppose you're taking the bound on both M and N and letting it grow. So you're, considering all M and N less than X, but they're relatively.
Yeah, I think, so typically it's still, right. So it's not as pronounced, but it's still typically that it almost never works in some sense. Like if you were letting M and N grow at about, if you were like, going through all pairs up to, with M and N up to X, right, you would still almost never have one of these representations. I feel like there's like a nice, like probably a really quick like counting argument you could do to get that. But yeah, there are some like more precise results in that direction. Yeah. So anyway, so for now though, I'm just fixing M. So Elsholtz improved this result a little over a decade later. So he showed that for all M, E sub M of X is at most is big O of X over root log X. And in addition, that if M is congruent to 0 or 3 mod 4, then that's actually the correct asymptotic. So, or I should say it's within a constant multiple of X over root log X. Note in addition, right, that phi of M, if M is bigger than 2, phi of M is also at least 2. So, this actually does improve on this bound for all M bigger than 2. And then, I guess, right, for M equals 1, you can actually show that you can always write 1 over N as a sum of 2 distinct unit fractions. So actually, so I said I'd answer your question on the next slide. It is actually, I try to answer your question on the next slide is a few slides later. But Elsholtz's results were improved pretty recently, actually, with this very complicated theorem, with a very strange result. So, or with a very strange looking bound. So let's say that M is bigger than 2. I'm going to define a constant called T. So there are 2 cases. If M is a multiple of 4, then T equals 1. Otherwise, we let N be, I'm going to write the prime factorization in this way, 2 to the R0 times P1 to the R1 times P2 to the R2, all the way up to PK to the RK, where these PIs are the odd prime factors of N. And in this case, T is going to be the largest number satisfying, or the largest number for which 2 to the T divides every PI minus 1. So
the P should be PK minus 1, right? Not PR minus 1.
Oh, you're right. That should be PK. I did not.
You don't end up using the R's either, right? You don't really need them for this formula.
Right. Okay. So this could have been, I guess, written more succinctly, but that's true. You don't need the exponents, you only need the individual prime factors. And then from that, you get that E sub M of X is asymptotic to this constant multiple of X log X to the 2 to the T minus 1 over log X to the 1 minus 1 over 2 to the T. And Cm is some constant that only depends on M. So we're seeing, again, this sort of almost always, or this condition that E sub M of X is still little o of X because we're dividing by a positive power of log X and only getting a positive power, or only getting a non-negative power of double log X on the top. And we can actually get Elsholtz's results from this theorem. So suppose M is congruent to 0 mod 4. Well, in this case, t equals 1, just because that was how we defined it. So we plug t equals 1 into here. 2 to the 1 minus 1, well, that's 2 to the 0 is 1. So raising double log x to the 0. So we just have 1 on top, and then we have root log x in the numerator, in the denominator. So x times 1 over root log x. And we get x over root log x as he said.
So I just want to clarify. So t is less than 1, p1 plus 1 up to pk plus 1. There was an r there. I didn't quite get how it's the last slide. So that should be pk.
That should be pk, yes.
Yeah, okay. Okay, I'm comfortable. Yeah.
Okay.
Now that I see the plot, I want to make sure I understand it.
That's good.
Thank you.
Sure. Okay. Next is, in addition, Elsholtz made the same claim for m congruent to 3 mod 4. In this case, 4, again, I put PR, I meant to write PK. 4 does not divide the GCD of P1 minus 1, P2 minus 1, all the way up to PK minus 1, because at least one of these primes is congruent to 3 mod 4. So in that case, let's say PI is congruent to 3 mod 4, then PI minus 1, or P sub I minus 1, is congruent to 2 mod 4. So it's not going to be a multiple of 4, but these PIs, all these terms are still even. So we get t equals 1 because 2 divides this GCD, but not 4. And so once again, we get x over root log x. And for other values of m, you could still show that it's, did I say greater than or less than a while back? It's still less than x over root log x because you're subtracting a different power. So yeah. So like, for example, for t equals 2, if t equals 2 instead of 1, you're dividing x by log x to the 3/4, so you're getting a smaller value, or if you're dividing by log x to the 7/8. So the x over root log x is the highest possible thing you could get, and it only occurs when m is congruent to 0 or 3 mod 4. So what if we fix n and let m vary instead? So this is an alternate version of the same problem. We get the reverse result. So in this case, m over n is almost never a BEF. So it almost never has one of these representations. So I'm going to define A of n as the number of m less than or equal to n for which m over n has a binary Egyptian fraction representation. And I'll let A star of n be the number of such m which are co-prime to n. So in a sense, you could argue that A star is actually the more natural quantity to look at because, right, if we were considering, summing this over many n, for A star of n, we're only counting each fraction once, whereas for A of n, it gets counted multiple times, because we would have m over n, and then we would have 2m over 2n later on, and 3m over 3n. So it would get counted multiple times if we're summing. So in that sense, A star of n is more natural. We also have Rov's theorem from earlier, which can be modified to apply to, non-coprime m and n, but it's still slightly easier to use with m and n coprime. So in 2000, these 5 people proved this result. So this was the work of Croot, Dobbs, Friedlander, Hetzel, and Papalardi. In particular, Croot has still been, doing a lot of research with the Egyptian fractions since then, but the 5 of them proved these 2 sums. So they obtained that the sum of A star of n over all n up to x is cx log x cubed plus big O of x log x cubed over double log x. And c is this very strange looking constant. So it's a quarter of the product over all primes p of 1 minus 3 over p squared plus 2 over p cubed, which turns out to be about 0.717. Note that this product actually does converge because, each of these powers, right, this 2 and this 3, are greater than 1. So we know the product is going to converge in the long run. It converges to this value. Actually, depending on how you define it, you could say that this actually double counts everything, because this sum, would count, let's say, a half plus a third, and a third plus a half as distinct fractions. So if we wanted to, so they're summing over all possible pairs n1 and 2, but if we impose the restriction that n1 has to be less than or equal to n2, we just divide c by 2 in the end and get about 0.35 or thereabouts for our constant. They're bound for A of n.
Wait, so what we're really counting here, again, is not the number of numbers, but the,
right.
the number, not the number of numbers that can be represented, but the number of representations, right?
Wait.
Or wrong?
Oh, wait, no, this is actually the number
of
numbers that can be represented. Yeah.
And is it true that most of them are only represented one way?
I don't know. I mean,
up to change of order, yeah.
So there is actually there's a neat theorem that I didn't put in this talk that actually does say that if m is bigger than 2n to the 2/3, then m over n has to have at most one representation. So it certainly seems like most of the time there should be one representation, just because that does encompass most possible, like most fractions m over n.
In some sense.
Yeah, in some sense. But yeah, I mean, so unless there's, then again, those fractions are also much less likely to have a representation, period. Yeah, so I don't know. So, but yeah, this sum only counts, only counts just the number of m where m over n is a representation. But yeah, and so the sum really does represent, every possible m over n with m and n, or with, m and n at most x, or, For A of n, though, the result is less precise. So they just got that it was within a constant multiple of x log x to the 4th. So we can see that that sum is less natural to work with, even though it is sort of the first one you would define. So A star of n being m and n co-prime, A of n being just m and n in general. And Huang and Vaughn, who we actually saw a few slides ago with the bound on the number of these fractions, or with the number of possible n with m fixed, where we can write these fractions, also worked on this problem. So in 2011, they reduced the error term in the first sum down from x log x cubed over double log x to x log x squared. So they really, did shave off a whole power of log there, just to make that result more precise. And so recently, for the past month or so, I've been looking at the moments of these functions. So in other words, what can we say about A star of n to the beta if we fixed some positive number beta? And this is to get a sense of how often large values of A star n occur. So how often do, I guess this gives you a better sense statistically of how often A star of n can be large. And this is the result that I have right now. And I might, be able to improve it in the future. So the lower bound is pretty straightforward because we use our condition on binary Egyptian fractions from earlier. So m over n has a binary Egyptian fraction representation if and only if n has two co-prime divisors u and v, such that m divides u plus v. And from that, we obtain our lower bound. So we see that A star of n is at least, So we see that A star of n is at least d of n plus 1 because I can just choose the pair u equals n, v equals 1. And in particular, any divisor of n plus 1 is going to be co-prime to n. So we get a star of n is bigger than or is greater than or equal to d of n plus 1. And this sum, the sum of powers of divisors is actually known. So the sum of the beta power of the divisor function is asymptotic to a multiple of x log x to the 2 to the beta minus 1. This was first written without proof by Ramanujan and then actually proved several years later by someone named B.M. Wilson. So
Hardy points out that it's very much inflated by the fact that there's a sparse set of numbers with many divisors. That's why when you take the power beta, you get a 2 to the beta in the bound, because it's sensitive to the fact that there's a small set of numbers with far more divisors than is typical.
right, yeah. So typically, yeah, you expect this to be much smaller. So d of n is typically log x to the log 2. So typically this, this quantity has I don't want to say a normal order because that's maybe that's a little more precise than it actually is, but it's typically on the order of log x to the 2 beta. So yeah, so these, these outliers really are doing that. And then here's just a sketch of, here's the idea of sort of my upper bound argument. So again, maybe it is maybe a little silly to actually, be doing all this, in the talk because I'm still working on it, but here's what I have. So the number of possible pairs u and v is at most d of n squared. So that's actually a little imprecise because we're also, assuming that u and v are co-prime, and this is just, how many choices for u are there, how many choices for v are there. So we get that a star of n is at most d of n squared times the maximum of d of u plus v over all of these pairs, u and v dividing n, that are co-prime. And so the goal is really to sum this quantity, d of n squared. This whole parenthesis should be to the beta. That's another little typo there. But yeah, the sum of d of n squared times the maximum of d of u plus v over all co-prime u and v dividing n. That whole thing raised to the beta. And so I actually bounded the sum with dyadic intervals. So d of n is typically 2 to the log x, or log x to the log 2. So for a given y, we can let s sub y be the number of n less than or equal to x for which both d of n and the maximum of d of u plus v lie in the interval 2 to the y up to 2 to the y plus 1. And then if we just sum over that interval, well, we have d of n squared and the maximum d of u plus v. This should say 2 to the 3 beta y. That's more typos in this thing than I thought. But yeah, so if we just sum over that particular, over the n in that particular set, we'll get that it's bounded from above by 2 to the 3 beta y times the size of s sub y. And then there are only going to be at most log x possible values of y. So the total sum is at most log x times this thing. And there are actually bounds on how often, the divisor function, lies in one of these intervals, or how often the number of divisors of n is bigger than 2 to the y. And I actually plug that in for y equals a constant c times log x. This quantity is at most log x raised to this complicated thing. So c times 1 plus 3 log 2 beta minus log c plus little o of 1. Then optimized c. So for y, you get 8 to the beta that this bound is largest when y is about 8 to the beta log x. And that plugging that back in gives us our desired result. And actually, I was working on this again earlier today, and I think I have some ways I can improve this. So I think I can bring this 8 down to 6. So not even really 6, a constant c sub beta that is going to approach 6 in the limit. So the sum of a star n to the beta is at most x log x to the c sub beta to the beta, where c sub beta approaches 6 as beta goes to infinity. And the two changes I made to that previous argument that I just mentioned are as follows. So we can use separate dyadic intervals for d of n squared and the maximum value of d of u plus v, because they are distinct quantities. So we would insist that d of n lies between 2 to the y sub 1 plus 1, or 2 to the y sub 1 and 2 to the y sub 1 plus 1, and d sub, or the maximum value of d of u plus v lies between 2 to the y2 and 2 to the y2 plus 1. And then also we can replace d of n squared with, I think for the number of pairs of co-prime divisors u and v. So going back a little bit, I'd still like to bring these exponents closer together, but right now it is looking like 2 to the beta and 6 to the beta over here. So this is, normally I guess I wouldn't necessarily, maybe give a talk about a problem that's still in progress, but these are the results that I have on this. Thank you.
Thank you very much. Are there questions for Noah? So you mentioned this, but I never understand these things very well. So what is the additional information you get by estimating the powers of the betas?
So I think it gives you just a better sense of the outliers, or at least I'm hoping it'll do that. So it'll give you it would give one a better sense of, how often a star of n is large. And so I haven't actually figured out, what you can say about that, but just what I'm hoping from like a statistical perspective.
I'm just curious, you formulated this in terms of moments and outliers. Have you actually produced any graphs? Do you know what these functions look like? If I gave you a large n, could you draw a graph where certain things would be obvious? Is that easy to compute?
No, I haven't actually done anything like that.
Because if I want to know what a distribution is like, I never look at the statistics first. I look at the distribution, and then I decide what it is I need support for. I mean, looking at the distribution, when you teach statistics, even when you teach elementary statistics, you emphasize to your students that there's no substitute for visual inspection. So I don't know what the programming is involved, because you have a lot of primes here and other things, but I'm sure if you look at this distribution, you wouldn't get any proofs, but you get results which are certainly true. You might also, like you just mentioned, outliers. That would be very blatant, but I have no idea.
I should say, for things like divisors, unless you're going to take very large numbers, you're going to be misled, because it takes a long time for the long-term patterns to emerge. Sort of naive, looking at the first 100 values, 1,000 values is going to mislead you. You really need that theoretical sense of, log n to the log 2 and things like that. You're not going to see those just from fiddling with the data. How
big does n have to be before you see that?
Again, the things I would tinker with where I do a few thousand values, it really wasn't obvious. I'm guessing you need to look at millions, or you need to spend a lot of time before you'll see what the theory can tell you. Just right at the beginning. Number theory is misleading that way.
No, that's a valid point. No, you work with these. What would the programming be like to see the first 10 million values of an AN or a star of n?
Yeah, so I guess what it would look, I would, I guess, try to start with like generating every possible, I guess I'd start with the fractions like 1 over n1 plus 1 over n2 first, then like add them up, right? You'd add up each pair and see what fraction you get and organize that way. I think that would be a lot better than, starting with a specific m over n and trying to get the fractions out like that, just because that way you're sort of avoiding having to actually factor anything.
Then you'd have two loops, each of a million, so you have a trillion iterations. You need something, you need to save something, but if we could work this out here, I'm sure I accept Moshe's point. It's worth that there's no point in looking at something misleading, but if we could think of some algorithmic way to get up to 1 million without using 1 trillion loops, that would certainly be welcome.
Yeah, I mean, so one possibility would be that you try to, this wouldn't give you the right answer, but I think it would give you something reasonably close, which is you try to loop over all m and n where, you know, you do 2 loops over numbers which have to be where the LCM has to be at most 1 million. So even though, yes, both numbers would be going up to 1 million, I mean, that's still a very significant restriction, you know, that the least common multiple has to be at most 1 million. The problem with that is, I guess you could be missing some numbers where, you know, let's say the LCM is large, but then there's, you know, some cancellation from between the numerator and denominator.
Anyways, it's worthwhile to think of, and I think I didn't realize Moshe's point, but it's certainly valid. You're not going to see a log n pattern from a few thousand numbers, but if you could think of some way of getting a slice of the graph, you know, I had a professor once, and he was commenting on doctoral theses at Harvard, and he said, it's remarkable what these people do without knowing what they're doing. And he said they're proving theorems which have obvious interpretations in you know, obvious applications, and that always stuck with me. He was working in neural networks. He was working actually in the brain. But the point here is, he made that point that, you know, it really helps if you can look at something. I realized that, you know, forget about coprime. Even looking at primes, you can be misled at looking at the first trillion primes and see all types of things that are not true. So anyway, it's a thought to think of.
Sure.
Other questions or comments on our speaker's talk, Egyptian fractions, or other bits of ancient mathematics?
So this is remarkable. This all came because someone bought a papyrus in Egypt in 1850. That's what motivated this.
Yeah, I was surprised. You know, when I really thought he'd actually dug it up. I thought it was named after the person who dug it up, but he just happened to. It said I'm basing this off of Wikipedia, which I shouldn't do. But no, he was in Luxor, and he just bought this papyrus from someone, and then he died 5 years later, and his family gave it to the British Museum, and they named it after him.
But this is not the only Egyptian mathematical text that's known. There is another. What's interesting about the Rin mathematical papyrus is that it's long. There's a lot of material in it. And there's another one called the Moscow Mathematical Papyrus, which is somewhere in the library in Moscow, which is also very long, but maybe less accessible to scholars. And then there are bits and pieces that have been dug up over the years. You know, I mean, it took a long time until scholars knew how to read hieroglyphics.
Is it true we have nothing from China because the ink fades?
So whether it's because the ink fades or they used, they wrote on fabric, linen or silk, which deteriorated with age. There was a while ago, 20 years, I'm not quite sure when, a discovery of some ancient Chinese texts. And one of the few non-Chinese scholars of ancient Chinese mathematics is my colleague at Lehman in the history department, Joe Dalbin, who has mastered Chinese and really has been spending the last 10 or 20 years translating and editing with a group of Chinese scholars these Chinese texts. He's very well known for he did his PhD in the history of mathematics, history of science at Harvard with I. Bernard Cohen, and he wrote a biography of, I guess it was Cantor, which is like the standard book. And then 10 years ago or more, he also did a biography of Abraham Robinson. which is also a very good book. But his real work is in ancient Chinese mathematics.
I know we have stuff.
He's actually come by our seminar at the Graduate Center, because he's not a mathematician. He knows some mathematics, but he's a historian, and he's in the history department at the Graduate Center also.
I know we have some stuff on magic squares from them.
Is there any natural question not in Egyptian fractions which would naturally lead to Egyptian fractions? Does anyone know of such a thing?
I don't.
I think you can, if you start thinking about the harmonic series, it like can lead naturally into that. So one of Erdős's papers, it's like, I think he starts from like looking at the harmonic series and then says like, well, what if you only did like arithmetic progression? So like, the fractions that are like 3 mod 7 or something like that. I don't know what he concluded.
Okay, yeah, or you want some partial, some segment of the series to, I don't know, simplify or to turn to be an integer. I see. Okay, yes.
Yeah.
So you could have, for that reason, you could end up looking at the question. I see.
Yeah, I think it is. I think the answer to your question is no one knows why the Egyptians did that kind of arithmetic.
Never mind the Egyptians. Why are we doing it? Are we doing it just because someone found the Egyptians doing it, or are we doing it, for other reasons?
Well, it depends on who's doing it and why. But
I mean, you could say it's fun, and that's enough of an answer. But
that's why I'm doing it.
Yeah, is there anything that leads to it outside of it? I mean, Goldbach conjecture presumably was originally motivated by the four squares theorem. So even, you can sort of see how you get to a question, even though it turns out not to be a useful approach. But
well, I mean, I don't know why. I mean, what?
Mel, I can make a
why do people care about solving polynomials and integers? I mean, it's,
I can make a suggestion, namely that I think like Pythagoras, all that sort of stuff was important in agriculture to measure land. So you needed to know squares and other things. And Noah mentioned at the beginning, if I want to know exactly the length of a third, I just have to divide a circle into 3 parts. That might be a lot easier than a fraction where, because they didn't have arithmetic the way we do. So if they wanted to get something exact, I would imagine 1 over n can be attained much more easily than some other number than 1 over n. For agricultural purposes, for measuring land.
That's true. The distinctness part of that just seems really weird to me then, right? Like, why do they care that the fractions, be distinct? Is that just to make it hard on themselves? Why not just write 2/3 as 1/3 plus 1/3 rather than...
It was just a theory.
No, it makes sense.
Fortunately, we're allowed to do what we're interested in doing, and no one knows. No one knows even what it means for something to be important in mathematics. There's no one knows. So yeah. I mean, it's like many other things. If you're interested in it and you want to do it, you do it. And if you're not interested in it, you find something else you're interested in and you do that.
Sure.
Only 100 years ago, they thought primes were useless.
Well, and the fact that they're useful is sort of irrelevant to me completely. Right? I mean, anyway. Too complicated. Easier to prove a theorem than. All right, everybody.
So I have
a speaker next week. Sorry, Christian, did you have a comment?
Yeah. Well, yes, I wanted to make a comment. Well, most of the questions on Egyptian fractions can be expressed in terms of Diophantine equations. And then, of course, there's the only distinction that in Egyptian fractions, the denominators are distinct. But if you, for most counting questions, how many solutions are there of that type, this does not really matter. That's more or less a small distinction, which when you count very large numbers of representations, it really doesn't matter. So to the question, where does it come from? If you go away from the history, you could come to the topic really from Diophantine equations.
But are you saying that you can translate a Diophantine equation often into some sort of almost equivalent Egyptian fraction statement?
Yes, for example, if you say you want to write the number 1 as a sum of k unit fractions, 1 over x1 plus 1 over x2, etc., up to 1 over xk, and if you count this, or if you have the extra condition that the xi's have to be distinct, the two questions are very closely related, and the order of magnitude will not matter, will not differ much.
Right, but that's just, you're saying there's not a significant difference between writing a number as a sum of n Egyptian fractions and writing a number as the sum of n pairwise distinct Egyptian fractions.
That's yeah, exactly.
Yeah. Anything else? Okay, Noah, thank you again. It was a great talk. And yes, and if we have a speaker, we'll meet next week.
Thank you for having me.
Someone to volunteer. Okay, take care. Stay well, stay healthy. Get your COVID booster.
Does it have to be on Egyptian fractions?
No.
I'd be happy to speak about about work I've done and a conjecture I found that has to do with resistances and triangular electrical grids, but E pops up unexpectedly.
Right, send me an email. Let me know.
Okay.
All right. Bye all.
Many thanks.
Bye, Mel. Thank you very much.
Bye, David.